Okay, let's talk briefly a little bit more about the geometric interpretation of vectors, and then we'll get to the operators, which is where all the fun is, and that's where all the power is, okay? So you remember that sort of the lowest level of that concrete to abstract continuum was where we can view the vector as a geometrical point in a coordinate system that humans can make sense out of, which is always going to be either 1, 2, or 3-dimensional, usually 2, okay? And you'll remember that I mentioned that a lot of times, instead of representing the point or the vector as a point in that 2-dimensional space, we represent it as an arrow, okay? So let me just draw that picture again. Imagine if we have a couple axes here, and we have a vector, and let's say our vector today is 3, 4. We can represent that as the point 3, 4, because we're going to go 3 units in that direction and 4 units in that direction, right? Or more commonly, we're going to represent it as an arrow here, where the arrow head goes up to that thing right there, okay? Now, one thing to understand with this picture, and this is going to come up a lot, is that a vector in this picture, and really more abstractly, even when we can't see the picture, has 2 things. It has a direction, and it has a magnitude. So the direction is essentially, we're going to represent that as an angle. Usually we say theta is what this angle is, but that's just basically showing that if I measure the angle from the x-axis up to this thing here, that tells me what the direction of the vector is, and there's a way to compute what that angle is based on what the coordinates are here. We'll go over that later. The important part now is to just understand that a vector has a direction, right? A scalar does not have a direction. A scalar only has a magnitude, but a vector has a direction and then also a magnitude, and the magnitude is essentially the length here, right? And maybe we call this r. It's typically what we use to refer to that magnitude, which stands for radius, because this is also the radius of a circle that's centered at the origin here, right? It's kind of an ugly circle, but anyway, you get the point. So every vector has a direction and a magnitude. Here's something a vector does not have, so I'm going to cross this out. It does not have a point of origin. And it's a little weird at first, but it's important that you get that. So I'm going to cross that out because it's not true that it has a point of origin. What I mean by that is this vector here that I've drawn here in red is the same vector as this one. And it's the same vector as this one. And it's the same vector as this green one. And it's the same vector as this black one. And it's the same vector as this other black one. Those are all the same vector. Because you see, a vector does not have an anchor point. The vector simply has a direction or a magnitude. So if I say the direction is northeast-ish, a little bit more north than east, and if I tell you that the magnitude is however long this thing is, I think it's going to end up being 5, then I've told you everything there is to know about the vector, and all the rest of it, as far as where I started it, doesn't matter. And that's important when we start thinking about things like a parachutist. So let's say there's a parachutist here who's coming down, and he has a parachute here that's preventing him from hitting the ground at too big a velocity here, right? One of the things that uses vectors a lot is physics, okay? So we might say there's a couple of different forces on this guy here. One force is this force dragging him down. That's going to be gravity, and that's pulling him down very, very strongly, that force. There's also another force, which is the wind, because maybe we got a crosswind here, right? And so we're going to say that, the wind is pointing him here. One of the things we're going to be interested in knowing is, how do those forces resolve? So if I want to combine those forces into one composite force, so I can figure out, hey, once you've already sort of taken everything into account, which way is this guy going to go? Which way is he going to drift? It's going to turn out that we're going to be able to come up with something like this, right? And that's essentially the sum of these different vectors here, right? And what we can do is we can say, well, let's add the 2 vectors up to find out what the composite force is on him. And what we can do to add them up, as I'm stealing a little bit of my own thunder here for the next segment, but just to understand it in a geometrical sense, to add those up, what we're going to do is simply add them tip to tail. So we're going to say, well, first go in the red direction here, and then go from that point over in the blue direction, and you will get the green direction. I really should have drawn this in green to start with, so I'll remedy that now by drawing it in green. Okay, so this is an ugly diagram to say the least, but what we're trying to show here is that the sum of the red and the blue vectors is the green vector. And the green vector is which direction he's going to go. So if I'm able to say, okay, this guy's falling, and this is my coordinate system, and right here is, this is sort of my base camp. I'm putting it here. So I'm sort of saying that the, x-axis is at the ground level. And I'm saying that the y-axis is centered on my observation tower here. And maybe somewhere this plane, dropped him out of the thing, and he started moving, and he has a wind, and he also has some speed from where the magnitude of the plane speed at the time, right? I'm making this very simple, but point is, once I drop this guy, then I can sort of say, where is he going to fall, and maybe I can compute where he's going to land. Maybe he's going to land right here, and I can compute how fast he's going to be going to see whether he breaks a leg or whether he comes out okay. All that stuff is possible, but notice, first of all, that the vectors I drew here had nothing to do with my coordinate system, right? I mean, this gravity is acting on this guy who might be at, position, 500 meters to the west and, 2,000 meters north, or not north, but up. And so it doesn't make sense to draw the vector starting from the origin, and that's because the vector doesn't really have a point of origin. It's just a force vector which is going to be applied to some object, which in this case is our guy. And in order to do the addition, we had to draw the red vector here, and then we had to draw the blue vector starting here in order to do this addition, in order to get us the green arrow. So anyway, all I'm trying to show here is that the point of origin of those vectors didn't exist. There wasn't any meaning to where does the vector start. We're just saying, hey, a vector's got a direction and a magnitude, and that's all it has. So if I add up two vectors, it doesn't really matter where the starting points are. I can freely move the vectors around so that I can do this tip-to-tail addition and get the version of the composite vector. And where this thing is going to land has nothing to do with where the ground is, or has nothing to do with where my observation tower is. It's simply a disembodied vector with nothing but a direction and magnitude at some point in space, and that's all I care about in terms of what the geometric significance of a vector is.